This conference will now be recorded.
Hello everyone. Today we'll discuss activity versus concentration characteristic of equilibrium constant. Then relation between Kp and Kc. So Kp is equilibrium constant in terms of pressure and Kc is equilibrium constant in terms of concentration. And also there will be related problems, and if time permits, homogeneous and heterogeneous equilibrium also we will discuss. So this activity versus concentration, what is the difference between these two? Some points we have already discussed in the last class. Okay, so activity mainly we use when we consider the non-ideality of a reaction, and concentration we can use when it is following actual ideal condition, because when it is practical condition it is mostly non-ideal. And why it is so? It is because of this different types of interaction, that is the interaction between two solvent molecules, or it may be one solvent molecule, one solute molecule, or it may be solute and solute, that is two solute molecules. So there, because of these different types of interactions, there is deviation from ideality in the reaction mixture. So concentration ideally we should not use, so we should use activity to account for this non-ideal situation. But you can replace activity by concentration. And how and when it is possible? It is possible only when the solution is very dilute. So activity can be used in place of concentration when you are trying to describe the behavior of real solution, but for ideal solution it is concentration. So activity for real, concentration for ideal, this is the difference. But mostly the solution we deal with, they are very dilute, so that is why you can easily replace activity with concentration, because when it is dilute, it is, you can ignore these type of interactions. Okay, so here activity of the substances, it will closely approach the formal concentration. Now activity, they are basically unitless. Now why it is so? Because they are actually ratio that compares an effective pressure or effective concentration. That means actual concentration, which is capital C, and in the denominator there will be concentration C naught, which is standard concentration. Similarly, if you consider effective pressure, that is actually ratio of P by P naught, and effective concentration is C by C naught. So as it is ratio, so the two units will be cancelled because it is the same unit, pressure unit or concentration. So that is why activities are unitless, because they are actually ratios. Now there are different ways by which standard state for different components of a solution we can define. So mostly the system, that is a common system that we follow. When we say standard state for gas pressure, it is basically P naught, and that is 1 bar, and you can also approximate with 1 atm, though 1 bar and 1 atm there is very slightly difference is there. It is not exactly same, but it is more or less same. Then when it is solute concentration, then C naught is mainly 1 molal for dilute solutions. And sometimes molality can be approximated with molarity also. So difference is, when it is molality, it is number of moles of solute per kg of solvent, and when it is molarity, it is per liter of solution. That is the difference. Standard state for liquid is pure liquid, and standard state for solid is the pure solid. So mostly when there is pure solid and pure liquid, we do not consider the term in the equilibrium constant expression. Fine. So these are the difference between activity and concentration, though mostly we deal with concentration, not activity, because we deal with dilute solution where you can ignore this type of interactions. Next is characteristic of equilibrium constant. So equilibrium constant, that is Kc or Kp, whether you are expressing it in terms of concentration or you are expressing in terms of pressure, it is having some characteristic. So we will summarize all the points. So what are the characteristics? It has definite value for every chemical reaction, and don't forget to mention the temperature. So whenever you are seeing any value of Kc and Kp, you also have to take care of the fact at which temperature the value is mentioned. Okay, because it is temperature dependent. When you are changing the temperature, the value of Kc and Kp will change. So that is why mention of temperature must be present. Now, what about the unit of Kc and Kp? Until now, we have not talked about the unit. So ideally, if we see, equilibrium constant is the ratio of concentration raised to stoichiometric coefficient. So suppose I am considering a very simple reaction, which is reactant R is converted to P. Now here coefficient is smaller, here coefficient is small p. So in this case, if I express Kc, it is basically concentration of P to the power small p, concentration of R to the power small r. Now concentration of P means what? It is moles per liter, and concentration of R is also moles per liter. So here see how the units are expressed. The unit of Kc is moles per liter, but don't forget this del N. Now del N means sum of stoichiometric coefficient of product minus sum of stoichiometric coefficient of reactant. Okay, so here we have taken a very simple example. So you have only one product, only one substance is product here, which is capital P, and P, depending on the value of P, it may be 2, 3, anything. Okay, so suppose I am saying that it is 2, so I am writing here 2, and suppose R is 3. That is the coefficient I am talking about. So in this case, what will happen? The unit will be moles per liter and 2 minus 3, which is basically the difference. Sum of stoichiometric coefficient of product. In this case, no question of sum because we have taken only one. But suppose there is P plus Q and so many other substances, then you also have to do the summation of all the stoichiometric coefficient that are present in the product side minus all the stoichiometric coefficient present in the reactant side. So in this case, it is simple, it is 2 minus 3. So unit is moles per liter, that is fine, but to the power this del N. Now when it is for Kc and when it is Kp, it is atmosphere to the power del. So in this way, unit you can understand. But we also, in the next slide, we will also see a detailed discussion related to units, because sometimes in mostly you will see units are not used for Kc or Kp, but in some textbook you can also find. So what is the discrepancy that we have to discuss in detail. But right now, whatever we have seen is that the unit of Kc is concentration unit to the power del N. And if it is Kp, it is ATM, that is pressure unit to the power del. Okay. Details we'll see later. Next characteristic, the expression for Kc or Kp may contain concentration of gases or molecules and ions in solution. But remember, this expression for Kc and Kp do not mention any concentration term or pressure term. Sorry, concentration term will be there because pressure is only for gases. So when it is pure solid or pure liquid, we should not use that substance in the expression for Kc. So what it is actually trying to say. So suppose here RR, I have not mentioned what is the physical state, but suppose I am saying it is solid and equilibrium sign, and P, that is gas, so it is okay. So in this case, basically, or if it may be aqueous also. So when you will write the expression for Kc, it will be basically only concentration of P to the power small p, but don't mention the concentration of R because its physical state is pure solid. And similarly, if it is written L in the expression, that means physical state is pure liquid, then also in the expression for Kc, that should not be mentioned. As it is discussed, remember in the previous slide, the last point, standard state for liquid is pure liquid, for solid is pure solid, so we do not consider it. Fine. Next point related to catalyst. Catalyst changes the rate of forward reaction and backward reaction equally, so there is no effect on the value of equilibrium constant. Okay, so whether you use catalyst or you do not use, it doesn't matter to the value of Kc or Kp. Then changes in concentration, pressure and temperature and inert gases Suppose you are changing the concentration in the reaction mixture, you are changing the pressure, you are changing temperature, or you are adding some inert gas like argon, helium, etc. Then they will affect the equilibrium. Now, when I'm saying affect the equilibrium, I'm not trying to say that it will change the value of equilibrium, but I'm just saying that the position of equilibrium will be changed. It will favor either forward reaction or it will favor the backward reaction. So in this case, you are getting P from R, and forward reaction is R to P, backward reaction is P to R. Now, when you are changing concentration or pressure, there will be some specific effect, and that will be discussed in detail under Le-Chatelier principle, which is we'll discuss separately. Okay. Right now, as a characteristic of equilibrium constant, just know this fact that if you change concentration, pressure, temperature, actually we already know that when you change the temperature, the value of Kc and Kp itself is changed. But when it is concentration, pressure, inert gas, the position of equilibrium is changed. Now, position means the yield of product that may be changed because the forward reaction may be occurring higher compared to the backward or the reverse. Okay, so details we'll discuss under Le-Chatelier principle. So may affect the equilibrium, favoring either forward or backward, but not equilibrium constant. Actually, not equilibrium constant when the sentence is ending like this. There should not be the mention of temperature, because when you say temperature, it will change the equilibrium constant value itself, not just the position. So when I'm saying position change, that means the value is not changed, only the position changed. But when I'm saying the value itself is changed, that means there must be difference in temperature. Then if equilibrium constant is greater, having some value greater than 1, suppose it is 25 or 20 or 10 to the power 3 like this, then equilibrium favors product formation. That means the yield of product, it will be higher. And if it is lesser than 1, then obviously now it will be mostly in the reactant side. So it means equilibrium favors the reactants. So once the equilibrium is reached, the amount of reactants will be high compared to product. Okay. So these are the different features of equilibrium constant. Now there is important note, and that is regarding the unit of Kc and Kp. So different disciplines and different textbooks, they treat units of equilibrium constant differently. So that is why you have to be very careful when you are figuring out that what convention is followed actually. It may vary. Often the convention change within a textbook. That is, in the same textbook, sometimes you may find that unit is mentioned, sometimes you will see unit is not mentioned. Okay, so it is not often stated explicitly also. So our purpose here is to see what is actually happening. So in the previous slide you have seen that there is some specific unit possible for Kc and Kp because it is concentration to the power del N or pressure to the power del N. Now what we do when there is no dimension, that is there is no unit, that is if you are finding in any textbook that there is no mention of Kc and Kp, and also the problems you will find in exam, you will see there is no unit mention for Kc and Kp. So what is happening here? Why the unit is not present? So what we are doing here, to make equilibrium constant dimensionless, we have to use activities. Remember, activities, it is a ratio. There is no that is the units will be cancelled. So if you use activities instead of concentration, it will be dimensionless. Now suppose if it is not possible to use activities, that is because mostly we use concentration, then also you can get dimensionless concentrations. But how? By dividing the concentration with the respective standard state. So basically we are doing the same thing. In the activity also it is a ratio of that is, remember what I have said in today's flash slide, it is either P by P naught or C by C naught. So same thing we are doing here by dividing the concentration with the respective standard state. So there will be same dimension. So dimensions will be cancelled out. Okay, ultimately it will be unitless. The common standard state for solute is a concentration of 1 molar. and the common standard state for solvent is the pure liquid. So you will see whenever there is any solvent mentioned, we do not use the solvent in the equilibrium expression. So what I am saying, suppose I am writing X in aqueous state plus H2O, which is basically solvent and it is liquid, and we are getting product Y. So in this case, when you will write the expression for Kc, it will be the concentration of Y, that is the Kc will be concentration of Y divided by concentration of X. We do not use the solvent. So here it is mentioned, that's why you usually leave out the solvent from an equilibrium expression because it is present as pure liquid. Similarly, even if you have any reactant where the physical state is mentioned as L, then also don't write it in the equilibrium expression. Unless we are using activities, all calculations are based on the assumptions that we are working with infinitely dilute solutions, because ideally activities should be used. But suppose activities are not used, simply concentrations are used. So by default it means that we are using very dilute solution, that is infinitely dilute solution. Now infinitely dilute solution means we are close to ideal situation. So when you are close to ideal situation, you can then replace activities with concentration. So if it is not specifically mentioned, then you have to understand that all calculations are basically based on the assumption that we are working with infinitely dilute solutions. Okay. So that is after that slide, whatever discussion we will do regarding Kc or Kp or the problems also that you will find, you will see we will not use any unit for Kc and Kp. And in most cases, that convention is mainly followed. In few cases, you can see the use of Kc or Kp, but not always. Relation between equilibrium constant for some reversible reactions are shown below. So in this table, what we will see, so this is also you can say characteristic of equilibrium constant. So the heading is same. So here we have taken this reaction. So suppose we are getting from A moles of capital A, B moles of capital B, you are getting C moles of capital C and D moles of capital D. So suppose if it is the forward reaction, and for this the equilibrium constant is Kc. So when you are just reversing the reaction, so reversing reaction means now you are considering as if this is the starting point. So that is why it is written in the left hand side. So we are calling it backward. So if for the first reaction equilibrium constant in Kc and you have reversed the reaction, now for this new reaction after reversing, the equilibrium constant will be inverse of the previous value. So if we take example, suppose from sulfur and oxygen I am producing SO2. So for this reaction the value of Kc is K1. Now if you reverse the equation, and if you want to know what will be the value of equilibrium constant, just reverse it. So now it will be 1 by K. So that is mentioned in this table. Similarly, the same reaction, suppose you are multiplying with a whole number or even if it is a fraction, both sides. So in this case, we are multiplying n. So suppose in this reaction, I am multiplying both sides with 2. So this new reaction that you are getting, now there will be power n. So see, original reaction is this one. So original reaction, now you have multiplied both sides n. So what is the difference? If you want to know the equilibrium constant for this new reaction, it is simply Kc to the power n. So here in this case, the value for that is this reaction I'm talking about. Originally, before multiplying with 2, originally it was having equilibrium constant 1 by K1, but after as I have done this multiplication both sides by 2, now it will be to the power 2 or 1 by K1 square, right? Now the next example is, suppose we are doing 4 individual reactions, separate, there is no relation. But here the product B, for the second reaction, now it is the starting material. And for the second reaction, the product, that is the starting material for the third, and the product for third, that is starting actually up to this point, that factor is fine. And the fourth reaction, as if now you are reaching directly from A to D. So in this case, so the first reaction, that is A to B, then B to C and C to D, you will see if you add all these equations, so what will happen? You are adding all these equations. So when you are adding, see, we have added B cancelled, C cancelled. So you are now left with the equation D. That means for this it is K1, for this it is K2, for this it is K3. And the fourth reaction, suppose for the fourth reaction equilibrium constant is K4. So equation 4 that you are getting by adding equations 1 to 3. So if you want to know the value of K4, that is actually you can get by multiplying K1, K2, K3. Okay. So we will apply this in this table, whatever we have learned. When we will solve the problem, you will see how we can apply this concept. Fine. Consider the following reversible reactions. Here we have reaction A2 gaseous plus B2 gaseous. Equilibrium constant is K1. You are getting 2 moles of AB, that is also gaseous. So this is equation 1. Now equation 2, equilibrium constant value is K2. And look at equation 2 very carefully. Now in the reactant side we have AB, which is the product of first equation. As if you have reversed it. And it is not simple reverse. There is also change in the stoichiometric coefficient, right? So we have to find relation between K1 and K2. So obviously if you want to get equation 2 starting from equation 1, the first thing that you have to do, you have to write the same equation by reversing it. So now I will write 2AB in the left hand side. I'm just simply reversing it. Okay, I'm not writing this G for simplicity. So A2 plus B2. So as you have reversed it, so for this the equilibrium constant should be 1 by K1, isn't it? Next, what we'll do, as the coefficient is different, we will multiply both sides by 3. Now it will be, you will be getting equation 2 after multiplying by 3. So when you are multiplying by 3, here also it should be that is the power, now it will be changed to 1 by K1 to the power 3, right? So now this equation is basically equation 2, which we have obtained from equation 1. How? By following 2 steps. The first step is you have reversed it. First step, just reverse it. The second step is multiply by 3. So we have followed these 2. In this way, you can get equation 2 from equation 1. So now we can write that K2 should be equal to 1 by K1 to the power 3 or 1 by K1 to the power 3 or K1 minus 3. So it is matching with option 3, right? So in this way, we can we have applied whatever we have seen in the last slide, right? Next problem. Following reactions, equilibrium constants are given as, so S plus O2, solid and gas, we are getting sulfur dioxide, K1 value given 10 to the power 52. There is another equation given, 2S plus 3 oxygen, and we are getting sulfur trioxide, K2 value given 10 to the power 129. Now there is a third equation, and you have to find the equilibrium constant for this third equation. 1, 2, 3, all are different. In the third equation, here also SO3 is the product, but starting material is SO2 and O2. Now this third equation, you can get from equation 1 and equation 2 by arranging it in different ways. So how you will arrange it? First of all, see the final equation, that is our purpose is to get final equation from 1 and 2. So 2SO3 is present in the right hand side. In equation 2 also it is present in the right hand side. So we will not disturb equation 2. We will keep it as it is. But see here in the left hand side we have O2 and we have SO2. But equation 1, SO2 is present in the right hand side. So that is why what we have to do, equation 1 somehow we have to reverse. Not just reverse. After reversing, you also have to multiply equation 1 with 2 so that equation you can get stoichiometric coefficient 2. So first write this equation in reverse order. So when it is reverse, it is SO2, S plus O2. I'm not writing the physical state for simplicity. So once you have done it, the K1 value that will be changed to 1 by 10 to the power 52, right? Now the next step, what you will do? Next step, you will multiply by 2. So when you are multiplying it by 2, there will be a square, which is basically 1 by 10 to the power 104. So suppose this is equation. Okay, I'm not giving any number. Next step, what I will do? Now I will add this equation. So if I add this equation, 2s plus 3o2, 2SO3. So now 2s will be cancelled. 2SO2 as it is here. And here we have 3O2, 2O2, 2O2 will come left hand side. So it will be only one oxygen. So see, now basically you are getting the final equation. So this is the final equation. And for this equation, as we have directly written it, we have not done any changes. It is simply 129. But you have added these two equations, and for the first equation it is 1 by 10 to the power 104, and this is 10 to the power 129. So overall effect, that is equilibrium constant for this reaction will be, so suppose I am writing it K3. So K3 is basically 1 by 10 to the power 104 multiplied, because you have added it, so there will be multiplication. 29. So 10 to the power 129 minus 104. So it is matching with option B. Okay. So we have arranged the third equation. We have obtained the third equation by arranging 1 and 2. So what we have done, we have not done any changes in the second equation. This is intact. But first equation, first we have reversed it, then we have multiplied by 2, then add it to equation 2. So that is why finally we are getting this calculation. So option B is the correct option. The stepwise formation for CuNH3 will be 4. Copper tetramine complex 2 plus is given below. So stepwise formation of CuNH3 2 plus, CuNH3 whole 4 2 plus. It means actually what? It means Cu2 plus 4 ammonia, and you are getting this complex. Okay. Now this equation, for this equation, it is basically the formation of copper tetramine complex. Now this equation can be done in stepwise manner. Stepwise means here I have taken 4 ammonia together. But suppose you have you are doing the reaction one by one. One by one means first you have taken copper 2 plus and you have taken just 1 mole of ammonia. and it is K1. First you are getting CuNH3, sorry, it is 1. 1 minute. Should there will be only one ammonia because we have taken it only one. So this is suppose equation 1. Then in second equation, in the left hand side, the same species, now it is in the left hand side, that is a product of equation 1. Now it is in the reactant side for equation 3. Equation 2. In the second equation, the second ammonia is taken, K2 is the equilibrium constant, and you are now getting CuNH3 whole 2. Now this is in the product side for the third equation. Now it will come in the reactant side, and we are getting CuNH3 whole 3. And finally, in the fourth equation, now you are getting the final product, which is tetramine complex. So if you add all these 4 reactions, what will happen? This will be cancelled because left hand side, right hand side. This species will also be cancelled. This is cancelled. Now what you are left with? You are just left with copper 2 plus 4 ammonia and this. Okay. So as we have added all these equations, so for this equation, suppose it is equation number 4. So for equation number 4, if I am saying that this is having equilibrium constant K, so K should be equal to K1 into K2 into K3 into K4, right? So if it is so, put all the values 10 to the power 4, sorry, there is a printing mistake, 10 to the power 4, then 1.58, 10 to the power 3, then 10 to the power 2, and again 10 to the power 2. So if you do this calculation, you will find 0.1, sorry, it is, first you will get 7.9 into 10 to the power minus 11. It is 1.58, it is 5 into 10 to the power 2. Okay, so this value for equilibrium constant we are getting. So power is 11 because it is 4, 3, which is 7, then 2 and 2. That means total 11. And 1.58 into 5, that will, let me do the calculation. .58 into 5. Yes, it is 7.9. But finally in the equation it is asking that the value of stability constant, okay, these are fine. Stability constant means for stepwise all the values are given. But finally it is asking the overall equilibrium constant for dissociation of this. But look at this equation. This is basically formation of copper amine complex. This is not dissociation of copper amine complex. Now when you are talking about dissociation, it is basically the reverse reaction. So if I reverse this reaction, what will happen? Now I will write copper tetraamine this side, and then I will write copper 2 plus and 4 ammonia on the right hand side. So this is basically dissociation. And for this reaction, it is the question is asking the value in this format. But this is basically formation. Both are not same. So for the formation, it is K value, which is 7.9 10 to the power minus 11. So for dissociation, the value should be K prime, which is reverse of K. So now I will write 1 by 7.9 into 10 to the power minus 11. So 1.7.1 divided by 7.9, this is actually 126.126 into 10 to the power 11, but you have to write it in this format. So if you change it to 10 to the power minus 12, it will be 1.26. You have to take rounded off to nearest integer. So this is basically x, which is almost equal to 1. So the answer of x is 1. Okay, so in this way we can solve this problem. Next important topic is the relation between Kp and Kc. So Kp expression for this reaction all are in gaseous state. Product side C and D with proper coefficient, and in the reactant side we have capital A and B with proper coefficient, that is A and small b. Fine. Now Kp expression, it should be partial pressure of C to the power raised to the power C, then partial pressure of capital D raised to the power D. Then in the denominator we have partial pressure of A raised to the power A and partial pressure of B raised to the power B. Now if it is so, then we also know, we come to this side, that pressure is basically equal to active mass into RT, or active, instead of active mass, better we say concentration into RT. Now if it is so, now all this expression for partial pressure we can convert it to concentration into RT. So we will do so for all the 4 species. So based on the above expression, the partial pressure of the reactant products can also be expressed in terms of concentration. So now it will be changed to concentration of A raised to the power A. The same thing for all the 4 substances. So in this equation, now I can write A to the power A, then RT to the power A. After that, sorry, it is C, then D to the power small d, and RT to the power B. Basically RT, it should be normal bracket because RT is not concentration, right? So you better we use normal bracket. And in the denominator it should be concentration of A to the power A, then RT to the power A, concentration of B, RT to the power B. Now C to the power C, D to the power D, A to the power A, and B to the power B. And RT terms we will write separately as if it is C plus D minus A minus B, A plus B, minus A plus B together. Now this term, that is the coefficient in the product side minus coefficient in the reactant side. So C plus D, small c obviously, minus A plus B, that is actually equal to del Ng, or simply del N. G is mentioned because it is gaseous state for all the substances. So this place you can write del Ng. Now look at this part. This is basically Kc, right? When we express in terms of concentration, we write it in this way. Directly we write the concentration multiplied by RT to the power del Ng. Don't forget to put this bracket because it is not T to the power del Ng. It is RT multiplied together to the power del Ng. So this is the relation between Kp and Kc. Now one thing is clear. If del Ng value is 0, suppose del Ng value is 0, both side coefficient, when you are doing this subtraction you are getting 0. So if it is 0, obviously Kp and Kc both will be same. Similarly, if del Ng is positive, that means Kp should be greater than Kc, and if it is negative, that means Kp is lesser than Kc. So these are the different possibilities we can get for the relation between Kp and Kc, provided there is del Ng value is 0, positive or negative, right? Now some examples we will see for these 3 different cases. So example 1, 1 mole of nitrogen, 1 mole of oxygen, you are getting 2 moles of NO. So here coefficient is 1, 1. So in this case, del Ng value is 2 minus 1 minus 1, which is 0. So in this case, Kp will be equal to Kc, right? Then another example, in this case, all are basically balanced. That goes without saying, because without balancing, you can't do this relation that this calculation is not valid. So first of all, you have to check whether it is balanced or not. So here I have taken balanced equation. So in this case, del Ng, product side you have 1 and 3. So it will be 1 plus 3. Reactant side you have 2. So it is 2. So it is 4 minus 2. So you are getting 2, and this is positive value. Now if it is positive, then Kp is equal to Kc. This is square. So it will be greater than the value of Kc. So Kp is basically greater than Kc. And the other possibility, del Ng, here stoichiometric coefficient is 2 in the product side. So 2 minus 2 and 1. So it is negative value. So if something is negative present here, that means Kp is equal to Kc RT to the power something negative. So it will be here. It is basically 2 minus 3 minus 1. So RT to the power minus 1 means it is actually Kc by RT. So in this case, Kp will be lesser value compared to Kc. So these are the different possibilities for the relation between Kp and Kc. In which of the following equilibria Kp value is not equal to Kc value? So one by one you have to check. Now for the first equation, here if you look at the del Ng value, it is 2. It is 2, but should I consider it? No, we should not consider it because it is S. Just have a look in the previous slide. Here all the species that we have taken, all are gaseous. So no other physical state is there. But in this case, you also have to take care of the fact whether physical state is S or L. So we will not consider this one. Only oxygen is considered. So it is 2 minus 1, which is positive. So it means Kp and Kc will not be same. Kp and Kc, we have to find that equilibrium where Kp is not equal to Kc. It may be del Ng value may be positive or negative. That is Kp may be greater than or lesser than Kc, but it should not be equal. So for the first option we are getting this. So this is basically the correct option. But why the other options are not correct, that we have to see. So see in the second case, all are G. So here it is 1. Here it is 1. This is also 1. This is 2. So 1 plus 1 minus 2. Here del Ng is 0. Right? Then come to the third one. Third one, all are gaseous. 1, 1, 1, 1. Here also del Ng 0. And the last one. Here also it is 1, 1, 2. That means again del Ng is 0. So that is why for all these three cases, Kp is basically equal to Kc. Only the first one is not equal to Kc. So option 1 is the correct option. Here we have a gas phase reaction, which is 2 moles of gaseous A. We are getting 1 mole of A2. And it is at 400 Kelvin. The del G dot, that is del G naught value given 25.2 kilojoule per mole. Equilibrium constant in terms of Kc. For this reaction, we have to find in this format. Something into 10 to the power minus 2, round off to nearest integer. And extra values are also given. Ln 2.3, then R value, universal gas constant, log 2, and 1 atm equal to 1 bar. Everything is there. Anti-log of 0.3, that is also given. Now, as this reaction is in gaseous physical state, see if we use this relationship, remember del G naught in thermodynamics we have seen del G naught is equal to RT 2.303, then it is log. I'm directly writing log, then it is Kp. So in this case, the equilibrium constant directly I'm writing Kp because if you write it Kc, it will be wrong because here it is mentioned gaseous state, it is mentioned already G. So from this del G value, it is given 25.2, but remember it is kilojoule, so you have to change it to joule. So it will be 25.200, right? And this side it will be 8.3 multiplied by 400, 2.303, and log Kp. So log Kp is equal to now here we have base 10. So the value that we'll be getting is minus 3.3. And this value, it means that Kp is equal to 10 to the power minus 3.3. Now here this anti-log value of minus 0.3 is given. So this you can break like this. Suppose you are writing minus 3.0 multiplied by 10 to the power minus 0.3. So 10 to the power minus 0.3, that value is 0.501. So I can write 0.501 into 10 to the power minus 3. So this is the value of log Kp, but we have to find Kc. Now remember the relationship between Kp and Kc. Here del Ng value is 1 minus 2, which is minus 1. That means Kp equal to Kc Rt to the power minus 1, or I can write Kc by Rt. Now Kc value you have to find. Kp you already know, Kp into Rt. Now Kp value is 0.501, R is 0.3, this is 400. So ultimately it is just multiply 8.34 and 0.501, and here we have 10 to the power minus 3, and here as if 10 to the power 2, so it is 10 to the power minus 1, 16.63. But we have to write it in this format, so it will be 166. So just compare, this should be the value here, but round off to nearest integer, so it is 166. So final answer is 166, right? Homogeneous equilibrium, and there is another term which is heterogeneous equilibrium. So homogeneous equilibrium means it is just like homogeneous mixture. So homogeneous mixture means whatever substance we have in the mixture, all are in same physical state. So when you are talking about equilibrium, the same logic will be applied. The equilibrium in which all the substances involved exist in single homogeneous phase. Then you can use the term homogeneous equilibrium. So here states of matter of products and reactions all will be same. So if something is aqueous in the right hand side, both the substance, then the left hand side also it will be same, because homo means same. In most cases, the solvent determines the state of matter for the overall reaction. So suppose if the solvent is water and the substances are soluble in water, then mostly in the bracket we write aqueous, AQ. Here we have some examples of homogeneous equilibrium. So the first one is in gaseous phase. So here you can see product side ammonia is gaseous, and reactant side nitrogen and hydrogen both are in gaseous state. Then the second equation, that we are doing in the solvent water. Now ammonia is written as aqueous because it is in water, and here it will take one proton from water, it will be converted to ammonia. If we balance it, it is NH4 plus, and HO minus will be there. But overall you can write it as NH4OH, but it will remain in this. If you consider the dissociated form of ammonium hydroxide, it is basically NH4 plus cation aqueous state, hydroxyl ion HO minus aqueous state. So here you can see this last statement. You will find the meaning here. The solvent is determining the state of matter for the overall reaction. Now for the third one also, here we have taken ethyl acetate. So this is basically H star, CH3COOET or OC2H5. So it is ethyl. This part is acetate, ethyl acetate organic molecule. It is H star. So ethyl acetate, it is reacting with water. Basically it is hydrolysis of H star. So when there is hydrolysis of H star, then we get acid and alcohol. So here this part is broken. So from this part you will be getting acetic acid, and from the other part ET you will be getting ETOH, that is ethyl alcohol. But here the solvent, it is aqueous media. So that is why H star, it will be in aqueous state because it is having solubility. And acetic acid, which is in the product side, that is also in aqueous state. So physical state is mentioned as AQ, and ethanol, that is also mentioned as AQ. So all these reactions here, physical state is same. So that is by both sides for all the substances. So these are examples of homogeneous equilibrium. Heterogeneous equilibrium, the equilibrium in which substances involved, obviously now it will be involved in different phases, and it is called heterogeneous because heteros means different. So suppose there are total 4 substances, and out of these 4, 3 are in same state, but only one is not in same state. So just one species, if it is not in same state, then also it is applicable. Because if you want it to be homogeneous, then all the substances should have same physical state. So just one is different physical state, it is enough to call it heterogeneous equilibrium. So one or more states within the reaction will differ. Some examples here we have calcium carbonate. Now it is in solid state. It is not having solubility, much solubility is not good in H2O. So though the solvent you have taken water, it will not be soluble. Then we have CO2. Now it is in gaseous state. Its solubility in water is not very high, right? Only high pressure, under high pressure it is soluble. And in the right hand side, basically it is calcium bicarbonate. You can also write the salt like this, CaHCO3 whole 2. But if you write it in a cation and anionic form, it will be Ca2 plus 2 bicarbonate. So cation and anion, they are in aqueous state because they are this salt is soluble in water, but not reactant side. The other two reactant, that is reactants CO2 and CaCO3, they are in solid state and gaseous state. So in this equation you can see all the different states, solid, liquid, gaseous, everything present, right? Come to the second one. Here ammonium carbonate is the only reactant present in the left hand side, and which is in solid state. Now after its decomposition you are getting 3 substances, all are in gaseous state. This is basically water vapor. So it is heterogeneous. And the third example, 2Mg, that is magnesium metal. Obviously it is solid, reacting with oxygen, it is gas. And we are getting magnesium oxide, which is again solid. Heterogeneous equilibrium often involve pure solid or pure liquid. So as you can see, pure liquid is present, pure solid is present. This is also pure solid. So in this case, when pure solid or pure liquids are involved, its concentration remains constant. That is, with progress in, when reaction is progress, there is no change in its concentration because it is in solid form. So it doesn't matter how much, no matter how much of it is present. So its concentration remains constant. That is initial concentration, whatever it is, as concentration doesn't change. So that is why it will not be present in the expression of Kc or Kp. For equilibrium in the aqueous medium, the concentration of solvent will not change appreciably because it is present in large excess. So this reaction you are doing in water, but water is present in large excess compared to other substances. So its concentration is not changed. So that is why it is not involved in equilibrium expression. And overall, what we can conclude? In general, pure liquid, pure solid, that is in this case you can see magnesium, magnesium oxide, then ammonium carbonate, and obviously solvent, that is water, can be ignored while writing the equilibrium constant expression. So that is all about heterogeneous equilibrium. And further discussion, you will be able to see both these examples. That is, we will deal with both homogeneous equilibrium as well as heterogeneous equilibrium. So that's all for this in this video. We are at the end of the session. Thank you for listening.